Well, good evening, everyone. Thank you for participating in this PEEC live streamed astronomy talk. Tonight, we have Dr. Nicole Lloyd-Ronning talking about black holes, and we'll start that in just a minute. A couple of words first. First of all, I should mention that tomorrow is the summer solstice, so have a super solstice over the weekend. And also, the PEEC has a couple of very short video presentations regarding the solstice on the website if you would like to look at that and see if you can find those presentations. Let's see. My name is Rick Wallace. I'm the president of the board of directors for the Pajarito Environmental Education Center, or PEEC, here in Los Alamos, New Mexico, and I'll be the moderator for today's talk. The Nature Center is currently closed, but we will have lots of ways you can interact and connect with nature. Check out the PEEC website, peeknature.org, for our Take It Outside initiative, especially for this closure, and for other live stream presentations like this one. We'll send you an evaluation form after the presentation is over, and we'll use your comments to improve future presentations. We're able to offer programming at this time because of our wonderful members and donors, and so we'd like to thank you for your continuing support. Just a few logistics tonight. After our live stream, our presenter, Nicole, will be taking questions via Zoom chat. To find the chat feature, look for the Zoom app menu bar. You may have to move your mouse for it to show up. You'll either see a chat icon in the menu bar or perhaps more or some dots. Click on that and see if you can find the chat. Type your questions for Nicole into the chat window anytime during the show, and I will relay the questions to Nicole. At the end of the show, we'll probably stop and have mostly a question and answer time. Dr. Nicole Lloyd-Ronning is an astrophysicist at Los Alamos National Lab, working on gamma ray bursts, the energetic and explosive creation of stellar mass black holes through the deaths of massive stars. She's also on the faculty at UNMLA, where she teaches a variety of physics classes for undergraduates. So let me just turn this over to Nicole, and I will stop sharing my screen so that she can share her presentation.
Thanks, all right. Nicole. Thank you. Can everyone hear me okay? Rick, can you hear everything good?
That's
okay.
Great.
Okay. Hi, everybody. I thank you so much for coming out and discussing black holes with me tonight. I think the way that this is going to go is I'd like to spend some of the time talking about black holes and some of the time, lots of the time, talking with you about black holes and answering questions and having a discussion. So I'm going to share my screen. So before I even start, I would like to acknowledge this very important day, June 19th, or as it's called, Juneteenth, which, as you may know, is the celebration of the emancipation of the last remaining enslaved African Americans in the US. So it's a big day today, and I was thinking about it a lot and participating in some of the celebrations. And as I was doing that, and as I was preparing this talk and thinking about black holes, I was thinking about what a luxury and a privilege it has been for me to be able to study black holes and to ponder things in our universe. And in light of Juneteenth and in support of the Black Lives Matter movement, you know, I want to really, before anything, acknowledge the ways that I've benefited as a white person from institutions and systems that are set up to allow people who look like me to pursue this path to the exclusion of others. And you may ask, what does this have to do with black holes? And I would answer absolutely everything, because as a very wise student that I work with named Valeria Hurtado was reminding me yesterday that humans do science. And what that means is that our experiences and our biases absolutely affect the science that comes out, the science that we learn in our textbooks. And who participates in the conversation and who doesn't absolutely affects the science. So, you know, the thing about that is that there's a ton, as you'll see, I hope, in this talk, and we'll discuss, there's so much that we don't know still about our universe. There's so much that we have left to learn. And I hope tonight that as we're we're talking about black holes and thinking about the problems we have left to solve, we can be also thinking about how we can work together to make sure that everybody's being included in the conversation about science, so that we can work together to understand our universe. And with that, let's get into it. So let's start by thinking about gravity, and I'm going to show you something maybe you've come across in your physics classes, or maybe you haven't taken physics yet, or never did, and maybe you don't plan to. But usually the way that people describe gravity, and certainly the way I learned about it when I was going through my earlier training, was that it's a pull between two massive objects. And that pull, that force, is stronger when if the objects are more massive. And I'll use this term mass a lot tonight, and all that means is stuff, atoms, things that are made of stuff. That stuff is mass. Okay, so anything that has mass gives a gravitational pull, and the more mass, the greater the pull. And also, the closer these masses are, the stronger the pull. The farther away they are, the less the pull is. So this is the way that at least I was taught gravity in school. And it's very useful, and the equations are straightforward, and you can calculate what you need to calculate for a lot of things. But I'm going to ask us tonight that we kind of put that picture aside a little bit, and let's rethink gravity. And in particular, what I want us to do is think about it in the framework of general relativity. And so that word, maybe you've heard before, maybe not. It doesn't matter. It's a term that is another way to think about gravity, and I'm going to describe that now. Okay, and what it requires is sort of thinking about space and time together as sort of a flexible fabric. Like picture a stretchy sheet, or say a trampoline or something like that. If we can imagine that we are living in space and time as a flexible fabric, then this is going to help us understand black holes a little bit better. Okay, so things like stars and planets and galaxies, which are just a collection of stars in the universe, can warp space-time and change its shape. Okay, so you might notice here in this two-dimensional image, the bigger ball, which we might assume is heavier, is warping that space-time fabric more than the lighter ball, say the red one there. So right here, I'm giving you the general relativity, the equation of general relativity in words. And that is that mass and energy, they're really equivalent. Mass and energy tells the space-time fabric how to warp. And the space-time fabric then tells that any mass and energy around how to move. This is the essence of general relativity. You can write this with an equation, so with symbols, but it is exactly this statement. That is what general relativity is. So I'm showing a little cartoon of that in 2 dimensions here. If we imagine space-time was this 2-dimensional sheet, that's what is going on here. Up in the corner now is an attempt at a 3D visualization of this, because we live in 3-dimensional space plus the extra dimension of time. So that's really sort of the correct way to think about it, is in 3 dimensions, but it's very helpful to have this 2-dimensional picture to kind of get an idea of what this flexible fabric is and means. Okay, so let me move on. So let's get right to what is a black hole. And it's fairly straightforward in terms of how you can kind of wrap your head around it in this picture. It's a lot of stuff, a lot of mass in a small volume. So if you come with me over to the upper left hand of this slide, and you see our sun in the space-time fabric, And you can see that it warps the space-time fabric somewhat. And you'll imagine, planets on that space-time fabric, that warping will cause them to be in orbit around the sun. And now if we can squeeze the sun down to, say, the size of the Earth, which is roughly this white dwarf picture here in the middle, you can see that squeezing that mass into a smaller volume causes the warping to be more severe. And so closer to that white dwarf, we're gonna get more of that gravitational effect, more of that warping that will cause our motion to be affected in a bigger way. And let's go even farther, and let's squish that sun down into the size of about, 20 kilometers across. This is a neutron star. If you do this to our sun, you would get a neutron star. And it's a very dense star. Again, it's about the mass of the sun and the size of, a radius of 10 kilometers or so. And you can see how much that's distorting that space-time fabric. And so now keep going, and I'll tell you in just a moment just how far you have to keep going. But if you squished even a little farther, you can imagine if you had an actual fabric and you put enough mass in a small enough point, that's gonna rip, right? It's gonna rip your sheet, rip your trampoline, rip whatever fabric you have. And that's one way to sort of envision what a black hole is, or how we can understand it in the context of thinking about gravity as the warping of space-time. And you can imagine that when you get past that hole, that rip in the fabric of space-time, you're out of space-time now. You've fallen through. You can't get back out again. So a black hole is a warping of the space-time so severe that anything that goes in can never get out. No matter how much energy you had, I can't get around the fact that I've caused a rip, or that it's so curved that no matter how hard I try, if I had infinite energy, I will just keep swirling around and never pop out of that hole again. It's inaccessible. So this is a way to understand what a black hole is in the context of general relativity, which again is just thinking about gravity in terms of mass and energy warping our flexible space-time fabric. Okay, so I'll give you a moment. That was all, general relativity in 2 slides. We're gonna kind of explore a little further what I mean by that. Let's go, just how much do I have to shrink our sun down, keeping its mass the same, to make it a black hole. So I'll remind you, the mass of the sun is 2 times 10 to the 30 kilograms, and I wrote it out because it's fun to see all the zeros out. Even though I love, of course, scientific notation, it's nice to see just how massive our sun is in kilograms. The radius of the sun is about 700 million meters. So if I can take that mass and I can squeeze it down to the size of roughly downtown Los Alamos, that's our sun would be a black hole. Okay, so that's our sun. What about something else? What about the Earth? The Earth is roughly 6 times 10 to the 24 kilograms, and it has a radius of about 6 million meters. And think for a moment, take a guess to yourself in your mind, how small do you think we'd have to squish all that mass of the Earth down? Into what kind of volume, roughly, would you guess, in order for it to be a black hole? And the answer is about a centimeter. It's about the size of a marble, okay? So all of this to say, again, that a black hole, we're going to talk about where we see black holes in our universe, but a black hole, a really nice way to think about it is just a lot of mass in a small volume. And this is kind of showing you, for objects that we're familiar with, like the sun and the Earth, how small of a volume are we talking about, okay? So before we get on to observations of black holes and how we know they're out there and why we know they exist, I just want to go over, emphasize something, because they're often talked about as really exotic objects in our universe. And in some ways they are. They're, that warping of space-time is pretty crazy and cool. but they're actually relatively simple compared to most objects out there, because there's only a few things that we use to describe them. One is the mass, as we've talked about a lot. And it turns out, because a black hole is defined by how much mass is in a particular volume, mass and radius are directly related. So if I know the mass, I know the radius. And if I know the radius, I know the mass. Another thing we use, it turns out pretty much everything in the universe spins around, and including stars and galaxies. And so black holes that we find in the universe have some spin to them, and we'll get to that a little bit later. So we describe them by their mass, by how fast they're spinning, and you can also describe them by how much charge they have. They can, in theory, carry charge, and by charge I mean electric charge, like when you have your feety pajamas on and you get all charged up and you shock yourself, that electricity, that's what I mean by charge. In reality, we don't think there are any black holes out there that are actually charged, because there's enough charges around in our universe that they would quickly neutralize. They would attract opposite charges, and those positive and negative charges would quickly become neutral. So really, for astrophysical black holes, and by that I mean black holes that we actually observe in our universe, we really only need to describe them by their mass and their spin. So that's nice. I like simplification. I like simple things. So I really love that about black holes. I appreciate that. So what I want to spend a few minutes talking about is, how do we know they exist? So we can talk about the general relativity, and that black holes are the warping of space-time and a solution to general relativity. And that's great. I can write all that down on paper, and it's beautiful and fun. But are they real? How do we know they exist, and how do we see them? So I'm gonna spend one slide reminding you how we see anything. How do we know anything about anything in space? And it goes back to days before we had any technology, and we just looked up. And we're stuck here, thanks to gravity, we're stuck here on Earth, and we're looking up at the sky, and we can't go out there and, to another star and do an experiment to understand how it works. We sit here and we look up at our sky, and we gather the information from our observations and try to make sense of it. And so what I want to talk about are the different messages, is what I call them, but basically the information that our universe gives to us as observers here on Earth, and how we understand things and piece things together from there. So the most common, the thing that's been used for forever and ever since humans have been in existence, in order to understand space, is light. We look up and our eyes receive light, optical light from space, or visible light. Space objects give us light of many different energies, or colors, you can call it. And here I'm showing you a picture of a supernova that happened in 1054 AD. And it's a picture. It's cycling through pictures that telescopes took that see different energies of light. So here's X-ray light, for example, and that's radio light here, and that's infrared and visible, and then here's the composite picture here. So it's kind of cycling through pictures that were taken by telescopes that see different energies or wavelengths of light. And it's giving us a different view of this one particular object as we gather the light from it. So this is the way that we usually think about how we do astronomy, is by gathering light from objects in space and then trying to make sense of it. But there's other messages that are given to us. And another way that we get information from objects in space is from particles called neutrinos. They're very, very light, and by light I mean not massive. They have a very tiny, tiny mass, And they're created in very special kinds of events, like when stars die and make a supernova. Maybe you've heard that. It's an explosion of a massive star. And lots of other processes in space make these neutrinos, and sometimes, you know, they stream toward Earth, lots of them all the time. The problem with these things is they're really hard to catch. They're hard for our detectors to actually grab them and detect them and measure their energy. But we can, you know, with these, if you get an opportunity, if you're not already familiar, to Google this word Kamiokande, or any neutrino detectors. There's another one called Ice Cube. In general, we need giant, pure water kind of detectors to catch these particles that are made in exploding stars and in jets around black holes. I'll talk a little bit about that later. So this is another message that tells us about some of the physics that's going on in objects in space. Another message or another piece of information we get is something called cosmic rays, which are very high energy particles. These are things like a proton, for example, from an atom that's been accelerated to very, very high energies in some really energetic process, like around a black hole, let's say. And it flies toward Earth, and it hits our atmosphere and creates a shower of other particles. We measure that, and we can infer something about the energy of that initial particle that came in. So this is another really important piece of information that tells us about objects out there, and including black holes. We think cosmic rays are made in some of the stuff that's going around, the processes that are happening around black holes. I'll get to that a little later. The last and very exciting message that I'm going to talk about today, and this is not exhaustive, there are other pieces of information we can get from space, but these are the main ones that we get from really far reaches of space. The last one is gravitational waves, and I know the PEEC has hosted many talks on this, and I think I've even given one or two about the detection of the ripples in the space-time fabric. So in some cases, with some objects, like two stars that are orbiting, they can cause that fabric to ripple, and we can detect that ripple. And that tells us something about the objects that cause the rippling to begin with. I'm going to come back to that a little bit at the end of the talk as we go through ways that we know black holes exist. So these are, when you may hear in the news sometimes this term multi-messenger astronomy. It's very much a very popular buzzword right now. It shows up all the time in papers and things like that. And when people say that, this is what they mean. Multi-messenger means getting more than just light from space, but getting particles like neutrinos and cosmic rays and gravitational waves. Okay, so keeping in mind how we understand what information we get from the universe, what it offers us as we're stuck here on Earth, you know, trying to figure out what's going on out there. Let's go on to black holes. And how we use these messages. So I'm going to start with what's usually the punchline in this kind of talk, and that is the direct image of a black hole. So you may have seen this last year or so, a collaboration called the Event Horizon Telescope collaboration, which is 1,000 or more people around the globe that are operating and using radio telescopes that are positioned all over Earth to take a picture of a black hole. And indeed, they looked at the black hole at the center of the M87 galaxy. This is about 54 million light years away. And it's been suspected for a long time. There's been a lot of indirect evidence that there is a black hole there at the center. But this Event Horizon Telescope used telescopes that see radio light to stare at this thing for a long, long time and put all their images and information together to create this very high resolution image of a black hole. And it is the first time we have ever seen that event horizon. So the little black darkness in the center, that dark circle, is the black hole, is that event horizon. and that's never been directly seen before. So it's you know, really for the first time ever, here we have a picture of a black hole. It's pretty amazing, and they're continuing to work on doing more of this, in particular looking at the black hole that exists at the center of our galaxy. So stay tuned for that. There's a lot of indirect evidence for black hole that we infer black holes are there. That's the stuff. I love that image of the black hole, but I love the indirect evidence too, because there's all kinds of really, really cool physics that goes on around the black hole that helps us understand that and infer that there's a black hole sitting there. So one indirect inference is through these objects called gamma ray bursts. There's two ways to make a gamma ray burst, and one is by having two stars collide, and in particular, those neutron stars that I mentioned earlier. If they swirl around each other and they collide, they can create a very bright explosion that we call gamma ray burst. And likewise, if you have a very massive star, say 20 or 30 or more times the mass of the sun, when it's done using up all its fuel, it's done shining, and it has no more fuel left to give to make it shine, gravity does its work to try to squeeze all the material down as small as it can. And if the star is massive enough, it can make a black hole. And in both of these processes, whether it's the two stars colliding or a single star collapsing, you get something that's called a gamma ray burst. And you really do get a bright flash of gamma rays for a few seconds or so, and then a bunch of other information along with it, which this is my particular field of study. And I could go on forever about this, but I won't. Well, there's other things to talk about tonight. But if you want to know more about gamma ray bursts, ask me. I love them, and they're really interesting. They have all kinds of physics. But what do these processes lead to? You're left with, in either one of those events, you're left with a highly spinning black hole in the center. And as gas is falling on it, there's magnetic fields that are being created in that disk and that gas that falls on it. And they get kind of wound up along the spin axis of the black hole. And this creates that jet that, oops, I meant to go play that again. This creates that jet that you see coming out, this sort of, it's spewing out stuff along that spin axis. And this process is efficient when you have a black hole at the center. So this is why we infer these gamma ray bursts are creating black holes. We also observe these very cool objects called X-ray binaries, where we have a star, say like our sun, just a regular old star orbiting around a black hole. And in some cases, if they're at the right distance from each other, some of the gas from the regular star gets fed onto the black hole. And you'll get this similar process where you get a jet of stuff shot out from the spin axis of the black hole. So this process too is called an X-ray binary. And this is another way we infer from the light that we see all around the black hole, we're inferring there must be a black hole there. There's also these very cool things called tidal disruption events. So sometimes a star will get near a black hole and the black hole will shred it. And we're going to get back to this at the very end. The process is called spaghettification, and it is what it sounds like. It gets sort of stretched out as it gets into that warped space-time of the black hole, and you see the light from the star getting shredded near the black hole. So these things, we're seeing more and more of them every day, and we understand it in the context of a star being shredded by a black hole. One of the very cool and to me most convincing pieces of evidence that there is a black hole is some amazing observations that were done looking at the center of our galaxy. We suspected there's a black hole there, but there was data taken over more than a decade. So up in the right-hand corner shows the years of data of observations going by. So it started at 96 and it's going to 2019. And the picture, the picture's showing is stars moving around. Oops, I'm sorry, I want to play that again for you. Here we go. So the stars moving around the galactic center, that little fake shape of a star in the middle is our galactic center. And you see these other little blue dots are observations of regular stars, and the way that they fling around that central point, that little white star shape, tells us how much mass is in that volume where that white star is located. And remember that a black hole is defined by a certain amount of mass in a certain volume. And the only, if we understand anything about our laws of physics, that has to be a black hole there. The way those stars are moving, how fast they are moving, tells us that there is a lot of mass in a small volume. And we're led to the conclusion that that has to be a black hole. So to me, these observations were amazing and very convincing. Like I said, stay tuned for information for the data from the Event Horizon Telescope that's looking at our galactic center and hopefully going to give us an image of that black hole. So, and another super cool, exciting, and incredibly convincing evidence that there are black holes before we got that direct image are from the gravitational wave messenger. So in 2015, the LIGO detector, which is, I'll talk about that a little bit more in a second, but it's designed to measure the ripples in space. And remember that we talked about how when two stars are orbiting each other, as they get closer and closer and they collide, they can cause a ripple in space. And in 2015, for the first time, LIGO measured that ripple, and the conclusion was that that had to be from two black holes colliding. I'm going to show you another video of it in this way. I like this one because as it plays, you'll see kind of a three-dimensional image of the rippling in space. That's this red, on the picture, this red ripples. So these are the gravitational waves that happened, that were given off. So again, this rippling of the space-time fabric when the black holes collided. Those ripples traveled across the universe to us, went right by Earth, and this LIGO detector, which I'll discuss in a moment, was able to measure that. So these waves are coming through us all the time. They're happening right now. They're very, very weak. They don't affect, we don't feel them ourselves, but amazing technology is able to detect them. And so I want to spend a moment talking about that because it's one of the new avenues, a whole new basically field of astronomy has been opened up through the detection of gravitational waves. It's a whole nother way to look at our universe. It's not light, it's not particles, it's ripples in that space-time fabric. And so this is a picture of the LIGO detector, and you'll see these long arms that are going at 90-degree angles from each other. This one, I can't remember. This one might be in Hanford, Washington. There's another in Louisiana. And then there are others built. There's one in Italy, and there's some being built really all over the world, in India, in Japan, in China. So the whole world is excited about this way of seeing the universe. I just want to remind you kind of what a gravitational wave you can kind of envision. It's not the way that I think of, say, a light wave, where it's just kind of an up and down motion. It's really stretching and squeezing, right? It's this really interesting ripple, as you see here. And so what does that mean for these lasers? So remember those long cement arms from the LIGO detector at 90 degrees, they have lasers inside of them. And those lasers are shooting at mirrors and then bouncing back. And basically what they're doing is constantly measuring the distance from, say, that beam splitter to the mirror. And the other beam splitter to the mirror. Okay, they're measuring that distance all the time. And up in the right and the left-hand corner, you can see as a gravitational wave goes by, it will squeeze space in one direction while it stretches space in another. And the lasers will measure that that ripple, that change in distance along that arm there. So when no wave is detected, the data might look like that. And when a wave is detected, again, the distance shifts a little, and the light waves of the lasers, when you bring them back together, they add up in a different way when you get a gravitational wave go by. In other words, the bottom line is they can use that light to measure the distance change between the beam splitter and the mirror as the gravitational wave goes by. And the technology behind this and the engineering that went into this just blows my mind, especially because I'm not the most careful person in terms of, like, when I build something, for my garage or for my kitchen or whatever, I make it functional, but it's not extremely precise. And this had to be so incredibly precise, to the point where, it's like measuring the distance to our nearest star, which is 4.5 light years away, to the accuracy of a human hair, something like that. It had to be so incredibly precise that it blows my mind. So it took a lot of years of work and a lot of work from thousands of people to make this happen. But they could measure these ripples in space-time from two black holes colliding millions of light years away, and I think that's amazing. So yeah, I like to shout out that it's an engineering marvel. So the last thing I want to mention before we open up just to discussing black holes is just the crazy things that can happen near black holes, according to us as observers from far away. So what do I mean by that? If I, on Earth, am looking at a clock that's getting closer and closer to a black hole, I will observe the time on that clock slowing down. So time, remember, I keep saying this term space-time. Space and time are intimately entwined in our universe. And when space is warped, time is warped as well. So near a black hole, the time actually slows down to an observer far away, like me on Earth, let's say. Remember, we talked about black holes spinning. And near that spinning black hole, space-time itself, the fabric, gets kind of dragged. It gets kind of closer to the black hole. It's spinning a little faster than farther away from the black hole. And that's actually fundamental to these jets that get shot out. Remember when I was talking about these gamma ray bursts and X-ray binaries, and you see these jets getting shot out along the spin axis of the black hole? That frame dragging is what allows us to wind up magnetic fields that are around, and they end up shooting kind of out along the spin axis. So space gets dragged around near a spinning black hole. And then, as we talked about with the tidal disruption events, you get this effect called spaghettification. In some cases, depending on the mass of the black hole, the gravity at, say, your feet, in the case of this astronaut here, is much stronger than at your head, and you'll get stretched apart. You'll get spaghettified, much like that tidal disruption event we discussed. So that said, I'm going to stop talking for a moment. I'm going to unshare my screen or stop sharing the screen and open it up for any questions you all have. So let's stop share. Okay.
Okay, great. Thanks, Nicole.
Yeah.
In fact, you do have some questions.
Oh, good.
I'll start with some that aren't maybe quite as detailed as some of the others. Do we see gamma ray bursts if the star collapses to a neutron star instead of a black hole?
Oh, I love that question. We think yes. So we're never sure exactly what's at the center. The consensus is that it should be a black hole, but you can definitely also get potentially a neutron star at the center. And there are lots of models out there and cases of gamma ray bursts, of which we have thousands and thousands of observations of gamma ray bursts. In some cases, it seems like there could be actually a neutron star instead of a black hole. And that has to do with how long the light lasts after the gamma ray burst itself. We see kind of longer lasting light that we think might be coming from a neutron star with a magnetic field that's kind of feeding into this jet for a long, long time? So that's a great question, and it's an open research question. There's definitely room for that in the observations that there is, in fact, a neutron star instead of a black hole. But in terms of the power that you get from the jet, most cases it seems to be that a black hole would be a better fit.
Okay, great. Let's see. Let's see if I can phrase this from Curtis correctly. It was mentioned that the gravitational wave passes by the Earth, but I imagined that it passes through all mass. Can you clarify this?
Oh yeah, I'm sorry, that was my bad. Yeah, it passes through everything. You know, the two black holes collide somewhere out in our universe, and it creates waves that go out in all directions, and it passes by any observer anywhere in our universe. So I'm being very Earth-centric and thinking about, like, as you know, as we understand it here on Earth, it passes by us for sure, but it passes by all masses out in the universe. And please, if I didn't get your question right and I misunderstood, let me know.
Okay. Do we see, no, wait, sorry. Could black holes account for any portion of dark matter?
I love that question. That's a good question. You know, people thought so for quite some time. It's a great idea because, you know, unless there's a lot of gas around them, we don't see them. The light doesn't emanate from a black hole. There were tests done especially in the 80s and 90s where we looked. One cool thing about the black hole, although, you know, we won't see light coming from within the black hole, even if there's no gas around it and I just have an isolated black hole that's just totally dark, it will warp the light that from any objects that are shining from behind it. So let's say I have a black hole in the galaxy just sitting there, there's nothing falling into it, it's not shining, but there's some stars behind it. Those, as the light from those stars comes to us and passes by the black hole, it gets warped. And it creates this, it can create a ring or it can create multiple images of the star. And they're relatively easy to see in data. They're called gravitational lenses, or gravitational lensing is what this is called. So we can actually test that. So what people did was look in, especially in the 90s, I remember this, they looked, you know, through our whole galaxy and measured how much of this gravitational lensing from potential black holes was happening. And it wasn't enough to account for dark matter. So although it will account for some portion, it doesn't come close, as we understand it, to account for, you know, nearly enough of the dark matter that we think is out there. So great question. And we could, you know, maybe we're missing something else about, you know, how many black holes are out there. Maybe there's something we're missing there. Our galaxy is unique in some way that it doesn't have as many. But the simplest, you know, answer, if we think we understand how stars form and this gravitational lensing effect, is it doesn't do the job. But it's a great idea.
Okay, the next one may take a little background, but do black holes have hair?
Oh, that's a good question. I think there's a book titled that, is there not? So there is this no hair theorem, and I encourage you to Google it because I probably won't go into all of the background there. But what I will say, this goes back to the question of what are the things that we can use to describe a black hole, and that is its mass, its spin, and its charge. And then in addition, caught up in this black holes having hair, which is really, I think, is a way to say, you know, can we see them other than the stuff around them? Can we, you know, see, is there any way we can access information from within that event horizon? There is something called Hawking radiation, which shows up, you know, in the news now and then, and it is a way to, I wouldn't really say see a black hole, but it is related to this no hair theorem, and it has some quantum mechanics wrapped in all of it. So I talked about this a little bit this morning, but I'll just say again, you can get a case where particles will come in and out of a vacuum for the briefest amount of time. It doesn't violate our laws of physics, as we now have incorporated quantum mechanics into our understanding of physics. And so if I keep it to a short enough time, I can get particles appearing from nothing for a short amount of time. That does not violate the laws of physics. And so if that happens, where particles are created from nothing for this brief time, if that happens right at the event horizon, one can fall into the black hole and one can escape to infinity, let's say, escape to some observer far away. And in order to be consistent with physics and conserve energy, and that means like not really, we can't really create over a long amount of time something from nothing. The black hole has to lose energy. So this is a way for a black hole to, it's called evaporate. And that this is something that, you know, is all consistent with the laws of physics. We write it down on paper. We have never observed it yet, and it's not a realistic process for black holes we see in our universe, because it takes forever for these particles to cause any measurable change in the black hole's energy. But anyway, definitely contact me after. We can talk more, no hair theorem and all that. That gets into some fun, heavy quantum mechanics stuff.
We actually had a related question asking whether that could, such evaporation or Hawking radiation could be observable.
Good question. For all the black holes I talked about tonight, I don't think so, in the sense that the radiation is just too weak for us to detect it. So to directly detect it, we wouldn't be able to. These radiation coming off of it is just so minuscule. And then another way we could, in theory, detect it is that it does decrease the mass of the black hole over time. So if we could indirectly measure the mass, and we could see that Hawking radiation is causing this black hole's mass to shrink over time, that would be another potential way to measure it. The problem is for black holes that are that we see in our universe, that are the size of a sun, or, you know, the mass of a sun or greater, that takes longer than the age of the universe, that measurement. So we wouldn't see it in astrophysical black holes. The exception to that is some black holes that could have been created in our very early universe. And we might, if they're very tiny, so it turns out the tinier the black hole, the faster the evaporation process goes. And we think that potentially in the early universe, tiny black holes could have been created in that hot soup that was around the Big Bang time. And there's that final point of evaporation can release some gamma rays. So people have some ideas about potentially detecting, these are called primordial black holes. There's been no detection so far. It's just in theory at this point. That it's one idea though. It's exciting, and keep it on my radar with all the gamma ray detectors out there.
Okay. Another question is, why isn't the center of the black hole direct image that you showed pitch black? It looks like there's quite a bit of light emanating from the center as well.
Yeah, that's a good question. That has to do with a couple of things. A lot of it is that the light, there's stuff around this black hole, and it's at a certain angle from us, and that light is being bent, you know, in the way that I was talking about, this gravitational lensing. So light from gas behind the black hole is being bent around the black hole and kind of coming in front of it a little bit. So it looks as if there's light coming from the black hole, but it's not light from that central object. That's a good question.
Okay. Is there a particle associated with gravitational waves? How fast do the gravitational waves move?
Oh, that's such a good question. Yes, we call the particle associated with gravitational waves the graviton. So much like we call the particle associated with light waves a photon, and pretty much, you know, everything in our universe is both a particle and a wave, including you and the particles that make up you. It's just that anything that's very massive has a wavelength that's so tiny it's not measurable. But for the gravitational waves, there is a corresponding particle description, and we name that the graviton. And they travel, gravitons, just like photons, are massless. They have no mass, and they travel at the speed of light. And this was confirmed with the gravitational wave detections that LIGO's made in the last few years.
Okay. Do black holes lead to a different dimension?
I wish I knew the answer to that question. So there's so many interesting things that we can think about and write down about what is going on inside that event horizon. As far as general relativity goes, that description of gravity, as we go into that event horizon, our equations kind of break. We get things like 1/0. We get infinities and things where we can't write the equations down anymore. But there are ways that you can write down that a black hole makes sort of a tunnel to another part of a universe. You've probably heard the term wormhole before if you've watched enough science fiction films. So there are ways that we can write down on paper that black holes can be kind of portals to other parts of the universe. But this is something that it's very like touchy and hard to make these things real, we call it stable, but what that means is that it's probably not likely that they exist. Those things aren't probably real. So as far as another dimension, who knows? There are theories now, you'll hear the term string theory, and that is a way to try to understand both general relativity and quantum mechanics in one unified framework. Right now, those two sets of equations don't match up. But there's a lot of work being done in physics to try to make all of our forces, or in other words, understanding quantum mechanical things and gravitational things in one kind of picture. And so string theory is one way to do this. And the one that works best has 11 dimensions. And how one envisions that, if you know, please tell me, because my mind can't. It's something I can write on paper. I don't know how to picture it, but it makes the equations work. And it's not, it's allowed. It doesn't break laws of physics. It's sort of the idea is that these dimensions that we don't experience are kind of rolled up and inaccessible to us. So I'm not answering your question. I know, and that is to say that there really is no answer at this point, and it's an active field of research. So hope you spend some time working on it too. We need some people thinking about that for sure.
Well, I'm glad you mentioned science fiction movies, because we have two questions on Interstellar.
Oh!
The first one is, how do you rate the scientific accuracy of the Interstellar movie?
Okay, so I'm gonna confess, I'm so sorry. I did not even see it, but I will defend myself in these two ways. I did read a journal paper on it, and I talked to Kip Thorne, who was the consultant on that movie. And so Kip Thorne won the Nobel Prize for work that he's done with general relativity. And he was the one that wrote this paper that I read about the accuracy of it. And overall, it's not perfect, but overall, it does a very good job of capturing what's going on near a black hole. But I encourage you to Google that question, and you'll be brought to some resources where that's really analyzed better than what I can say, since I did not see that movie. I've seen about 2 movies in my life, and I think one of them is Jaws, and the other one might be Star Wars, and that's about it. So I'm terrible to ask about this.
Okay, well, let's see. I think you can handle the next one even without having seen the movie. We'll see.
Okay.
One of the things that I've noticed about Interstellar was from Kip's talk that he actually gave in Los Alamos last year. He was showing some slides showing that the view of the black hole from within the movie is probably the most accurate presentation that's ever been done on film. But the director decided to change Kip's simulation slightly to make it more dramatic. So even that has just a slight bit of fuzz to it.
That's right.
But anyway, when it gets to the end and they start looking in the library in the center of the black hole, I got to bow out of that one. I just don't understand that. Anyway, moving along. Okay, so in this movie, the characters spend time on a planet so close to a black hole that time passes more slowly for them than for their partner on the spaceship, which you've talked about, actually. Could a human safely get close enough to a neutron star to experience time more slowly than someone farther away?
Yeah, in this, I mean, well, okay, so there's two layers to that question. We'd have to get to our nearest neutron star, and right now our technology for space travel wouldn't allow that within our lifetime. So but if we could get ourselves near a neutron star, we could get to a point where we're close enough to the neutron star to have this measurable effect of time slowing down. And in fact, we have that effect on Earth. We account for that with GPS satellites. So GPS satellites have to account for the fact that time is being warped around Earth's gravitational field. And it's minuscule compared to what it would be like near a black hole or a neutron star, but it's actually matters. It matters, and we have to correct for it. So it's not even that you have to be near something as exotic or as strongly gravitational as a neutron star or black hole. It's a measurable effect here, even here on Earth. So it's real, and that's something it's fun to look up. That's a big issue with GPS satellites, is making sure that time is corrected for general relativistic effects. So general relativity affects our everyday lives. At least I use my GPS all the time.
All right, that's true. Okay, can you expand a little bit about your discussion of supermassive black holes, like in the center of M87, and a stellar mass, more normal black hole?
Yeah, absolutely. Yeah. So right now we have more definitive evidence of these two varieties or mass classes of black holes. So the supermassive usually are around 1 million to 1 billion times as mass of the sun, and we think those began forming in the very early universe when stars were forming. We think the stars in the early universe were much more massive than the stars that are forming now, like in our galaxy. And they were kind of these seeds of these supermassive black holes. So let's say you started with a star that was 100 or 200 times as massive of the sun, and it collapsed to a black hole, and more gas. The universe was smaller in the past, in the early universe. So things were crunched together more, and gas was falling on this black hole. And it grew over time throughout the 13 billion years of the age of our universe to be supermassive, to be 1 million to 1 billion times as massive as our sun. So that's one variety, and it's a very active field of research, exactly how those supermassive black holes grew and formed to begin with. And there's some open questions there that are really fascinating. The other variety are these so-called stellar mass black holes that are formed in these processes like gamma ray bursts, or two stars colliding. Those come from sort of the death of a single star in the little bit later universe. So we have these black holes that are around 20 to 60 solar masses, and then we have these black holes that are 1 million to 1 billion solar masses. And so there's this huge region in between that. Are there any black holes in that realm? And if not, why not? These are called intermediate mass black holes. This is another very active field of research that people think there should be something in that realm there. But we haven't seen any very strong evidence for it. There's a few hints that there's some of these maybe 1,000 solar mass or 10,000 solar mass black holes, but we barely have any evidence for that. So I don't have a great answer for why that is, because like I said, it's still ongoing field of research of why that, we're missing evidence of that mass range. Yeah, so lots to learn.
Okay, well, actually, here's a practical question right along those lines from Avery, who is 9 years old, by the way.
Oh,
I'd
hi.
like to know, how far away is the nearest black hole?
Ooh, that is a great question. I would guess that, I don't know the answer is the first thing I have to say definitively. I would have to look that up. But that we have them in our galaxy in these X-ray binaries. And I would guess that it would be maybe somewhere around 1,000 light years, but I could be wrong. Somewhere in our galaxy, there are black holes throughout our galaxy. So it's got to be less than the distance of the size of our galaxy, but it's probably not as far away as the edge of our galaxy. So that I don't really know the answer to.
Actually, I've got a little information on that.
Oh, please share. Thank you.
The closest supermassive black hole, of course, is going to be the one in the center of our galaxy, Sagittarius A star, which is about 25,000 light years away. But there is a black hole orbiting V616 Monocerotis, there we go, which is 3,500 light years away. So your 1,000 light years was very close.
Okay, good. All right, there you go. Well, thank you, Rick. I appreciate that. I'll remember that for next time. That's
there
good.
You go. Do you have any thoughts about the existence of white holes?
Only what, a little bit what I was saying earlier about what we can write on paper about, say, wormholes. And you can, the other end of a wormhole, you can name and write down as something called a white hole, which is kind of the opposite of a black hole. Everything exits a white hole. And this is, again, something that we can write down on paper that doesn't violate the laws of physics, but that we have no evidence for at all, and that it looks like in our actual universe, with all the things going on in the gas that's out there and the processes that are happening, it wouldn't be stable. We wouldn't be able to actually, create one of these, or nature wouldn't be able to create one of these in the universe. So my feeling is they're very cool mathematically, but I'm not holding my breath to actually seeing one someday.
Yeah, there's actually the same mathematics that suggests that there could be a bridge between a black hole and the white hole, the Einstein-Rosen bridge.
Right.
That same mathematics suggests that as soon as actual matter starts to go into the bridge, it closes off.
Exactly.
So, okay, one more question and one comment. I'll mention the comment first, which is a good one, that Kip Thorne actually did write a book about his experience on the Interstellar movie. And the scientific accuracy and simulations that went into that. It's written at a pretty high level, but if you have a background in physics, you might find that interesting. And then the last question is, if I back up to it, is there any scientific thought that dark matter might just be a scapegoat for misunderstanding the universe?
That's a great question. And we should always ask ourselves that every single day. I mean, definitely, I think that to think that we really, know what's going on. This goes back to what I was saying at the beginning about how there's so much that we have to learn. And, dark matter has been this mystery for a long time of what is out there that appears to be out there, to be making things move around as quickly as they do, but not, but we can't see it. We should ask ourselves every day, are all our assumptions correct? Are we misunderstanding something fundamental? My feeling, my personal opinion on that is that I think there is something there. There is dark matter of some sort. I think I'm so overwhelmed by how well the general relativity does in describing so many things across so many different kind of length scales and mass scales, that I feel like it's a very good description of gravity, even if it's not completely complete, let's say. And so in that sense, because it's done so well and been tested and verified so many times, that leads us to the conclusion that there should be, that this dark matter is actually some sort of mass out there that we just can't see. So my opinion right now is that I feel dark matter is a fair way to think about what's out there in the universe. But again, you know, we don't understand a lot, and it's good to question whether or not we really have our fundamentals right. Maybe there's something there. It's great.
All right. Well, great. Thank you very much. This has been Nicole Lloyd-Ronning talking about black holes on behalf of PEEC. And I'll just mention that we do have additional upcoming talks. You can check peaknature.org to see what's happening over the next few weeks on Fridays at 7 o'clock. So thank you everyone for tuning in, and have a good evening.
Thank you all. Thanks for the questions. Thanks, Rick. Bye.